Hello, everybody, and welcome to this webinar regarding measurement of noise from UAS, unmanned aircraft systems. So first of all, I would like to take some practical things. And first of all, you're all muted, so you can't speak with me or with some others. But you're welcome to write any questions you may have on the small box that you have to the right on the screen. You have a small folder called questions. There you can file the questions, and in the end of this session, I'll be answering as many as I can. You will also see that you have a folder called handout, which means that you can actually download the presentation. We are also doing a recording of the content, so if you would like to have a recording of the session, you're also welcome to get that. So this session will be roughly 45 to 50 minutes, and then it will be a couple of minutes more for questions. And the topic I'm going to cover today, it is measurement of noise from UAS. And you might say that noise from UAS, that's quite simple because it's very similar to noise from other flying aircrafts or from vehicles in the air. But I will show you in this presentation what is the differences and why is this more difficult to actually do accurate measurement of noise from UAS. So let's start with first a agenda for the presentation. So we will do, or I will do, a small introduction first. Then we'll speak about different types of aircrafts and what is the similarities and what is the differences. We will talk about different types of setup or configurations for measuring noise from flying vehicles. And we'll cover microphones over a reflecting plane. We'll cover ground board with inverted microphone. We will also cover ground board with flush mounted microphones, and we'll also touch a little bit on psychoacoustic recordings. Everything will then end up in a conclusion, and then it is open for questions. So let's start. And first of all, I would just like to introduce the company that I'm representing. We are a group of companies, and this group is called Axiometric Solution, and it is consisting of 3 different companies. It is AP, GRAS, and IMC, and we are experts in different areas. We are experts in precision microphones, productive test and measurement systems, but also electronic audio and electroacoustic test instrumentation. We are today owned by Battery Venture, which is a venture company from US, and we have a global platform where we are selling all our products from, and that is called the Axiometric Solution, consisting of the 3 brands, and we are represented all over the place in North America, Europe, and Asia. We have own offices in a number of locations, but also representations by distributors in some others. So what do we do? Well, you have a physical signal in the world somewhere, and then we are supplying sensors. We do measurement software, we do data acquisition instrumentation, we do the analysis, and that is giving you, the customers, the insight of the physical signal on this side here. So we are trying to solve issues in the R&D world, but also in different areas. As you can see here to the right, you will see that we're working in many different areas or segments. And what we are going to focus on today, it's going to be sensor part, and it's going to be aerospace and defense. So there's where we will find the UAS, UAVs, and we'll talk about that in the rest of the presentation. So just to put a little bit into perspective here, GRAS is a company founded by the Danish acoustician or acoustic pioneer Gunnar Rasmussen. And Gunnar Rasmussen, that is actually the acronyms, the two first letters in GRAS. It is Gunnar Rasmussen Acoustic Society. So that's the reason why GRAS is called GRAS. What we do? Well, we provide a number of different measurement microphones and precision microphones, and also fixtures to the industry. So what you see here, it is some standard microphones, measuring microphones, but also fixtures for testing headset, headphones, telephone sets, and whatever you have. So we are located in Denmark, and there is where we have our R&D and manufacturing. And myself, my name is Lars Winberg, and I have been working for the company in a number of years. Has been in the noise and vibration for the last 35 years. And I'm working as a business development manager for automotive, aerospace, and defense for the company. So that's a little bit about ourselves. And now we are going to go over or walk over to the topic for today. And first of all, why is it important to measure noise from airborne vehicles? Well, there are several reasons for that. And one of the reasons it is that all the flying vehicles since the 1960s has been certified. And as you can see here, you have different stages, which means that there are different requirements on the aircrafts. And we started out in the 60s with stage 2 aircrafts. There is where you had the Boeing 707, for example, and then it has continued to tighten up the noise legislation for different types of aircrafts. And today we are talking about stage 4 or stage 5 aircrafts, and they are then less noisy than we had back in the 1960s. In order to do these kind of certifications, we need to have accurate measurements on the noise coming from different types of aircrafts. There is also another topic, and that is legal requirements for airports. So if you go to an airport today, most likely they have a number of noise monitoring terminals around the airport, which is 100% or 24/7 measuring the noise around the airport. And they have a legal requirement to fulfill. They have an environmental capacity, and they are not allowed to actually override the limits on that. So of course, when you have this certification scheme, you have a legal requirement for a number of airports, then you need to know exactly how to measure accurately and repeatability of the measurements in all different airports, in all different nations, and so on and so forth. So first of all, just take a look at different categories of aircrafts. And if you take a look here, we have what we call subsonic jet airplanes. That is the commercial jets that operates in most of the airports today. We have also fixed wing propeller driven. That is what you see here on the picture. We have helicopters, and we have lightweight and UAS, small multi-rotor unmanned aircraft systems. So these are the most common categories, and you will see that the legislation is also sort of connected to the different types of aircrafts. The reason why it is that they have different characteristics, the noise from the different flying vehicles, and therefore they have different types of legislation. So let's go through the different noise characteristics of the three most common noise sources around airports and helipads. So if we take the subsonic jet airplanes, this is where you have a distance between the noise source and the receiver. is fairly long because these subsonic jet airplanes are operating in commercial airports, and therefore they have a pretty far away from people living. They are fast moving, so the noise source, are fast moving. The frequency content, it is below 10 kilohertz, and the reason why it is that it's a fairly long distance, and therefore the air in between the aircraft and the receiver is actually dampening the high frequencies. So that is the reason for that. It's also limited tonal content for subsonic jet airplanes. When you take a look at propeller-driven airplanes, the distance between the noise source and the receiver is, I've been writing here, medium. It's shorter, typically shorter than the subsonic jet airplanes. They are flying lower altitude and so on and so forth. They're also slower moving source, and the frequency is still typically below 10 kilohertz, but they have a tonal content. And therefore they are a little bit different when it comes to measurement of noise from them. When it then comes to lightweight and small multi-router UAS, they have a different characteristics, because first of all, the distance between the noise source and the receiver is short. You could have a landing area on top of a roof or a rooftop, where it is very close to the people living in the top floor of the house. So you have, first of all, the distance is shorter or very short in some cases. It is also a stationary source, because a UAS can be hovering, and a hovering UAS is equal to a stationary source. The frequency content is also higher. It can actually go up to over 10 kilohertz, and that is of course because they are closer to the receiver, and therefore there are not so much damping of the high frequencies, and therefore it can be quite annoying with the frequency, the tonal content. So as you can see here, there are sort of a different characteristics of the noise, and therefore we need to have a little bit of a background how the different standards that are existing has actually been evolving. So I'm going to start with the most perfect setup for all kinds of flying air vehicles. But first, a little bit about, there are a number of different rules and regulations. The first one is an EU regulation. We have the ICAO Annex 16, or CAA, or Federal Aviation Authority Annex 16, which is the environmental part, the volume. And this is divided into subsonic jet airplanes and also propeller-driven airplanes. And right now it is a new standard under development, and that is an ISO standard, the 20906. Oh, sorry, I was taking it a little bit too fast here. This is actually a very old standard. It is actually the ISO standard that was taking over after ISO 3891, and this is taking care of unattended monitoring of aircraft sound in vicinity of airports. So I'm sorry about that. This is an existing standard. It's not a new one. So this is just a small take on all the standards and regulations. But when it comes to the microphone configuration, it is pretty simple, and it is pretty equal in all different standards. And therefore, I have been trying to categorize them a bit. So if you have seen a noise monitoring terminal around an airport, you will find that the mast for the microphone is roughly 6 to 10 meters. Most installations are having 6 meters, because that is of course easier than erecting it 10 meters. And the reason why it is that some of the standards are actually dictating 6 meters minimum. When it comes to jet airplanes or commercial jet planes, There, the standard for certification is talking about 1.2 meters or 4 feet about the surface. And when it comes to propeller-driven airplanes, then we talk about upside-down configuration of the microphone configuration, and then the lightweight and small UAS. This standard is not yet finalized, so it is under construction. So I'll go through the different setups here, the configurations, and I will tell you about the different pros and cons for the different setups. First of all, you have some disadvantages with some of the installations here. If you take the microphones over reflecting plane, that means that you have a microphone, you have a surface on the bottom here, and then of course you have some interface or interference, ground interference from the ground. But if you're coming up 6 to 10 meters like this one is erected, then the ground interference is a minimum. If you take this one 1.2 meter over ground or over the surface, this is introducing some ground interference. In order to get away or get around that, the next standard is talking about a upside down configuration where you have the microphone on top of a known surface or a plate, and that is not giving any ground interface, but it will be some other disadvantages on this configuration. And then, of course, this lightweight or UAV standards is going to be something different because the three existing ways of doing it is not very practical or useful for UAVs. If we go into a little bit more detail and starting with the first installation, this is the 6 to 10 meters installation. And this is actually having almost a free field condition because the reflection from the ground is so far away from the microphone. So it is only the direct wave coming from the noise source that is picked up by the microphone and reported into the analyzer software. So it is close to a free field condition, but unfortunately, this is mostly for fixed installations because it is quite expensive and unpractical to have a 10-meter mast when you do just a test campaign for something. It's very difficult to erect that size masts. So even though it is a free field condition, it is a little bit unpractical, this one. The second setup that I'm going to talk about, it is this Annex 16, ICAO or FAA, Volume 1, Appendix 1, 351. This is talking about how we are actually doing these certification of aircrafts. And as you can see here, there is a reference, sideline reference, where you should have some microphones. We have a cutback reference with another microphone, and we have an approach reference where you're also having a microphone. And the standard is telling that it should be 4 feet or 1.2 meter above the ground. It should be a free field microphone of 1/2 inch microphone. So if we do that, we actually introduce some disadvantages because now the reflecting wave will actually reach the microphone and it will be combined with a direct wave. So that means that dependent on what sort of material, the surface, the ground surface, what sort of material it is, it will give you some type of reflective wave going into the microphone and disturbing your measurements. And if we just take a look and a little bit closer to this, and we take the worst situation, and that is if the noise source was 100% fixed, 90 degrees angle to the microphone, because then the wave will go down into the surface and it will bounce back and it will give you a reflected wave to the microphone as well. So what is happening when we are simulating this it's actually going to give you a what we call the comb filter effect. So if we are changing the frequency from 0 hertz and up to 10 kilohertz, you will see a octave spectra of this size. So what is actually happening here, it is that we can calculate for a 1.2 meter above the ground, we can actually calculate that we will have a minimum or a dip here at 71.4 hertz. And then you will have a maximum at 143 hertz, and then it will just continue like this. That means that we have a big influence on the reflective wave, and therefore this is not really a good measurement because you will have different result dependent on what frequency you're actually measuring at. So what is that actually meaning? That means that if you have a frequency where you're interested in a tonal content, you can have some situation where it is coincident with the comb filter minima that will reduce the signal of 20 dB. And you can also have some frequencies where it's actually amplifying the measured data with 6 dB. So dependent on the frequency, if you're interested in the tonal content, this will give you some challenges because you don't really know if you're measuring the real signal or a reflected wave. So this is another takeaway of this. It is that if we take overall the signal here, we can see that the sound pressure level measured at 1.2 meter height will be 3 dB higher than the corresponding level if you're using a free field condition. And that is, you can actually see it on this curve here. It is actually going to give you a 3 dB extra. And this 3 dB extra, it is the reflective wave that is interfering with the signal, with the actual noise coming from the noise source. Then you might say that this is, of course, just a theoretical calculation. And it is not going to be that bad if we are actually doing it in the field. Because there you have maybe a soft forest ground, or you can have a hard reflecting ground. You don't really know what sort of material you're using or having a surface. So we did another simulation, and we were using COMSOL, and we were doing a simulation where we had, in one case, we had soft forest ground, which is a flow resistivity of a low value, and then we had a hard reflecting ground where we had a times 1,000 higher resistivity. So that means that this experiment would then show whether we have the same issues with the soft forest ground compared to the hard reflecting ground. And the result of that, it is this picture. It's a little bit busy, but I will try to show you here. On this axis, it is the total sound pressure level. On this axis, it is the height over the ground. So 1.2 means 1.2 meter equal to 4 feet. So this is where you can see the difference on the sound level when you were measuring on hard ground or soft ground. So even though you see a difference, it is still giving not a perfect result. So it will influence your measurement even on very soft ground. So if you are on a football court or something like that, it doesn't matter. You will still have the effect of the interference from the soil. And this curve is actually showing here, the closer you are coming to the ground, the more influence you will have. So at 0.2 meter, you will have a bigger impact on the reflecting wave. So having said that, you then might say that, well, this is for the worst situation. This is Hoover condition. This is where we are standing just 90 degrees over the microphone. What about now when we have a moving source? And we actually had, for the jet airplanes, we had a fast moving source. And you are perfectly correct, because if we are changing the elevation angle here, then of course you will change the comb filter effect, and therefore it will sort of even out the effect of the comb filter. So if you're not interested in tonal content, and if it is a fast moving source, this is actually quite a good measurement. So therefore, if we take a look at summing up here, we said that for subsonic jet airplanes, the distance between the source and receiver is far or long. It was a fast moving source, frequency up to 10 kilohertz, and limited tonal content. Therefore, it is a pretty good measurement when it comes to larger aircrafts. So reflection is an issue for slow and stationary noise sources. And we should keep in mind that compared with free field measurement, the result will be roughly 3 decibel higher. We have some reflections, and therefore, if we are looking for tonal content, then it is a risk that we're overestimating or underestimating the frequency content. And we also found out that there are no major difference between hard or soft surface. So for subsonic jet airplanes, the first standard that was actually made for measuring from flying vehicles, this is a pretty good measurement because it is fitting with the characteristics of the noise from the aircraft. Then if we go into the next part, this is for the propeller-driven airplanes. This is the next part of the Annex 16, the FAA, Annex 16, Volume 1, Appendix 6. This is describing what they called an upside-down configuration of the microphone. And as you can see, we had a little bit different characteristics of the noise from the propeller-driven aircrafts. We were introducing some tonal content, and even ICAO or Federal Aviation, they recognized that when they were writing the standard, because they write the specified ground plane microphone configuration is greatly minimizing the interference effect of reflected sound waves inherent in pole-mounted microphone installation. For a 1.2 meter or 4 feet microphone, such effect typically occur in the frequency region that is most significant for the propeller-driven aircraft noise. So they recognize that this first configuration with a 1.2 meter is not going to work very nicely with a propeller-driven aircraft. And therefore they introduced a new type of setup or configuration. And if you just take a look at this, and I'll just go through the theory first, because as you can see here, this is an upside down configuration. The microphone is pointing directly to the surface or this plate here. So the theory of this, it is that if you're mounting a microphone flush behind a plate, so it is 100% flush with the surface, and this is a pressure microphone, then you have a reflecting ground plane. That means that you will measure a pressure doubling on this point. So it will be plus 6 dB on this point. However, they also recognized when they were writing the specification that this is a very difficult installation because you have a pencil-like microphone mounted under a plate with a cable going out here. So for practical considerations, they said, well, we can't really use this method because then we have to dig a hole under each individual plate in order to have space for the microphone, the pencil-like microphone. So they said, why not place it on top instead? Because the pressure, the sound pressure in this point, it's equal regardless of what direction the microphone is pointing. So they said, okay, let's try to put it on top instead and see whether we can adjust the air gap so it is measuring exactly the same as it was a flush installation from the backside. So the standard came up that the air gap has to be the half of the microphone diameter. And if you take a half-inch microphone, it's half-inch or 12.7 millimeter, and the air gap between the microphone membrane and the surface should then be 6.35 millimeter or roughly 7 millimeter. So in the standard, it is written 7 millimeter for a half-inch microphone. And then, of course, you still have a problem because you're putting the microphone in the sound field, and you're also having a fixture on the side in the sound field here. And therefore, I'm going to try to show you what sort of advantages and disadvantages it is with this setup. First, it is this fixture here. You have the microphone, you have 7 millimeter air gap, you have it not centered, you have it a little bit off center. So first of all, the sound pressure, it will vary over the surface of the plate. And therefore, it is quite important to find the spot where it is giving the most flat response over the entire frequency range. So I have some simulations of that, and I will show you why it has been selected 3/4 radius, which means 15 centimeters from the center. So that is 5 centimeters from the side. It also has to be a very exact air gap between the microphone membrane and the ground board. We have done some measurements and showing that, and I'll show you that in a couple of slides. And the microphone in itself is now positioned in the sound field, which means that that will also influence the measurements. So let's take a look at the first issue. That is the position of the microphone. And we have been simulating using COMSOL this plate, and we have been moving the microphone to different positions. So if you take a look at this curve here, you can see the blue curve. That is actually the center point. So this is the low frequency, 500 hertz. This is 10 kilohertz up here, and that you can see that it is varying over the frequency range. So it is not a very flat response if you're putting it directly in the center of the plate. The red curve here, that is the stipulated position in the standard, which means a radius or 0.15 centimeters from the center point. And that is giving a much flatter response. And you can see here we have been using 94 decibel, and then it is a pressure doubling, which means that it is measuring 100 decibel. So we have been simulating, and the result is that the center point is not that flat. The point where it is selected, the off-centered point, is much flatter. The second test we were doing, and this is actually a measurement, we were taking this plate and we were doing this upside down configuration, and we were taking a look at 10 kilohertz and we were changing the air gap. So we were altering the air gap from 4 millimeter to 7 millimeter to 9.6 millimeter. That is not very much. So we were interested to see what is the difference on the different air gaps. So if we take a look at the green curve, that is the air gap, that is the standard prescribing of 7 millimeter. So you can see here it is flat up to 1000 hertz, 5000 hertz, and then up to roughly 10 kilohertz. And then it is dropping off here. If we are changing the air gap, only having 4 millimeters, there you see it's starting to be offset already at 4 kilohertz or something like that. And then it is going up to plus 3 decibel, and then it drops off. And if you take an air gap of 9.6 millimeter, there you can see that it is dropping off too fast. And if we just take a fixed point at 10 kilohertz, you can see that the variation is actually 9 decibel between the different air gaps. So what is that meaning in practical issues? Well, in practice, when you're actually doing the measurement, what you have to do, you have to place the upside down microphones around in a large area, in a big area. And before the test, you would like to do a verification of your microphone and cable, and therefore you would like to do a calibration. You take your calibrator, you're lifting off the microphone because you can't really do the calibration when it is upside down. And then you have to fix it again with exactly the 7 millimeters air gap. If you're missing that, you can't really trust your measurements. So it is very important that you're actually fixing it to 7 millimeter, not more, not less, just 7 millimeter. The other test we were doing, this is also a test, it is not a simulation. This is actually where we were putting one reference microphone below the plate, and then we were putting different types of microphones on top here. So we were using a 1/8 of an inch and 1/4 of an inch and 1/2 inch. And of course, our idea was that if you put a smaller microphone, then it will disturb the measurement less, and therefore you would have better result than for a 1/2 inch microphone. But in contrary, you can see the curves here, and this is the test that we were doing. And if we start with a 1/8 of an inch, you can see that is the blue curve. That is actually almost flat up to roughly 10 kilohertz, and then it is starting to drop off. 1/4 inch dropping off at 10 kilohertz, and 1/2 inch dropping off a little bit before 10 kilohertz actually. So the conclusion here, it is that regardless of what size of the microphone you're using, the measurements are not really useful about 10 kilohertz. So let's take a look at the characteristics for these propeller-driven airplanes. It was distance between noise source and receiver was medium. It was a slower moving source. It has a frequency below 10 kilohertz, and it had some tonal content. And as we have concluded now, the reflection is not an issue any longer. And compared with free field measurements, the result will be 6 dB higher. Then the air gap of 0.5 times the microphone diameter, it is extremely important, and you will have good measurements of tonal content up to 10 kilohertz. And measurements about 10 kilohertz is not really possible. So this is also fitting very nicely with the propeller-driven airplanes. So now we have actually two different standards, and they are pointing in slightly different setup of the microphone, but they are good for their purpose. Now we are coming to the next part, and that is the lightweight and small multi-rotor UAS. And there are a number of studies being done right now and a lot of testing being done right now. And it is quite important that we know how the noise is actually behaving over a surface when you're doing it. So right now there is a new standard that is coming up, and this is called the General Requirement of Noise Measurement of Lightweight and Small Multi-Rotor Unmanned Aircraft System, UAS, which is an ISO standard, and it is a working group called 5305. And you can actually go on the internet and see what is the status. But to my top of my head, the status is that it has been out for commenting for all the member states, and they are working on the second or the third draft right now. So of course, we have seen that the way that we were doing the testing for jet airplanes and for propeller-driven aircrafts is not really going to work out, because as you can see here, this is the characteristics of the noise. The distance is short. It is a stationary source, which means that we can't really use this 1.2 meter because of the reflections. And the frequency range is over 10 kilohertz, which means that you can't really use the first method or the second method, and then it has a tonal content. So in order to make a good measurement for multi-rotor or UAS, then of course it is necessary to find a new method or an improved method of actually doing the measurements. So there is also another issue. You can say that, well, UAS, they are very small, and therefore you can test them in an anechoic chamber, which means that you can have almost free field conditions. That is possible for smaller drones and UAVs, but the problem is if you're having a little bit larger UAV or UAS, they needs to be tested in outdoor environments. And the reason why it is, of course, safety issues, because you don't want to have a drone, a very big drone, in an anechoic chamber. And that goes also for some of the smaller UAVs, UAS. And therefore, you are basically forced to be outdoor to do the measurements. And then you have the issues with the reflecting plane. So the problems we are facing, it is that we can do some measurements in anechoic chambers, but noise from the larger UAVs, they needs to be tested in outdoor environment. What we have said it is that free field conditions requires a distance between the microphone and the reflecting plane of 6 to 10 meters. This makes it difficult to install and costly. If we're using the 1.2 meter or 4 feet above the ground, that will introduce reflections, and that is not really good if you have a stationary source or if you have tonal content. Then we can also use this upside down microphone, but that is not going to work for frequencies over 10 kilohertz. So regardless of what we already have on the standards, it's not really useful for doing accurate measurements on UAS. So many years back, it was actually 6 or 7 years back, we were working together with NASA, we at GRAS, and we were developing a microphone that is sort of basing the idea from the theoretical ground plate that we saw. If you remember a couple of slides back, we were talking about the best way of doing it was actually to mount the microphone from behind a plate, but that was not practically possible because of all the microphones at that time was pencil-like. And now we have been working on different form factors for microphones. So we have developed a pressure microphone that is basically flat, and therefore we can put it from the backside, so it is 100% flush on the plate. So we have used the same geometry of the plate. It is still the same dimensions. And then we have put the microphone from behind instead. And that will give no interference from reflections from the ground. It will be suitable for measurement of tonal content. It will have a flat frequency response from 3.15 hertz up to 20 kilohertz. And there are no moving parts or fixtures. So you can't mess up the 7 millimeter. It is small in size. It's only 40 centimeters, and it is easy to transport and install. So the microphone that we have put in to this construction, it is this flat microphone, where we have taken the preamplifier and we have another form factor on that. So we have still a capsule, the microphone capsule, and a preamp, and then we have the CCP or ICP connection to your analyzer or test system. What we also are getting here, it is a pressure doubling, because this is the same situation as the upside down configuration. So we use 1/2 inch pressure microphone for this setup. What is also a very good advantage, it is that we actually have an adapter where you can put it on the microphone directly, and you can do a field verification or a calibration directly on the plate. So we can use the pistol or we can use a calibrator to put on top, and we can do the calibration verification of the measurement chain just before we are going live and do the measurement. So everything from what they already had in the standards, but it was difficult to actually make, we have made into this this microphone. And you might ask, is this in operation? Well, I said it was developed 6 years back, maybe 7, and it has been used for multiple tests in different conditions, different configurations. And the latest, you can see some videos on the internet. You have this NASA mobile acoustic facility that was doing a test campaign together with Joby Aviation, using more than 50 of these microphones spread out over a larger area to do a noise categorization of the noise from the Joby Aviation UAV. So in order to sum up, I have this picture, and this is the second last slide. So it's soon time for some questions. So if we take the 4 different methods that we have gone through in this presentation, we had the 6 to 10 meters free field condition. We had 1.2 with a reflecting ground. We had 7 millimeter air gap with a pressure microphone. We had a flush mounted pressure microphone. So this is a free field condition because the no reflections is going up to the microphone again. So this is suitable for all 3 different kinds of flying vehicles. If you take the 1.2 meter configuration, then it is suitable for subsonic jet airplanes with a plus 3 dB. It's not really suitable for propeller-driven airplanes because you have the tonal content, and it is not suitable for lightweight and small multi-rotor UAS because you have this, sometimes it is hovering and standing 100% still, and sometimes you have frequency content that are higher than 10 kilohertz and so on. The 7 millimeter pressure microphone on as a upside down configuration. This is suitable for subsonic jet airplanes. It is also suitable for propeller-driven airplanes, but it is not suitable for lightweight and small multi-rotor UAS because of the frequency content. If you remember, this upside down configuration is disturbing the measurements above 10 kilohertz, and therefore it is not really a good solution for the UAS. If we take this flush mounted pressure microphone on the plate, this is suitable for all 3 kinds of vehicles, and it is giving you a 6 dB higher value than for a free field condition. So as you can see here, it is pretty important to know what sort of microphone setup that you have been using in order to compare data, because you can't really take a measurement from a noise monitoring system and compare it with a upside down configuration, because you don't have this pressure doubling on the free field condition. So this is sort of giving the conclusion of the entire presentation here, and I only have one more little piece of information here, and that is I have now been talking about legislation and a way of objectively compare data from one side to another. This is the way that you have to do the measurement. But of course, there are also another type of measurements. It is also psychoacoustic measurements. And when it comes to psychoacoustic measurements, then it is much more interesting in putting a human-like body in place of where you would like to record the noise or the data. So GRAS is having a number of different setups for this. This is a head and shoulders where you have artificial ears and you have a ruggedized tripod, and then you're erecting this one to a human height, and then you will get all the reflections from the ground, and you will have the ear canal included in your measurements. So you're actually doing a detection of what the human person is feeling or getting into the eardrums. So this is much more a subjective measurement, but in some cases it's quite important to take this into account as well, because when it comes to a human being is going to hear this reflecting sound that is reflecting from a concrete floor or a soft ground and so on. So dependent on what sort of measurements, what are you going to use the data for, it is quite important to know how you're actually going to set up your configuration, your microphone configuration. So then I hope that you have been collecting or having some questions, because now is the time for questions. So if you have any, you can just write them in the box. And I see here I have actually 2 questions already. And the first question, it is this ISO standard. When do you expect this one to be valid or confirmed by all the member states? Well, it's always difficult to tell exactly when a standard is going to be released. My best guess would be that it is released within 1 year, and this standard is going to take care of anechoic chamber measurement from UAVs, but also for outdoor environment. And it will probably most likely go in a direction where the microphone is mounted beneath or underneath a plate like I have shown you here. Of course, I cannot 100% promise that this is going to be the standard, but it's quite obvious that this is the direction the standard is going into. The second question, it is regarding the plate as well. It is asking if we are using a 1/2 inch microphone and why it has been selected a 1/2 inch, why not a 1/4 inch or a 1/8 of an inch microphone beneath the plate, because usually that will give you higher frequency range. Well, we have taken the 1/2 inch because that is closest to the standard for the upside down. And this will give you a frequency, a flat frequency response up to 20 kilohertz, which means that you have a good measurement over the hearing range of a human being. So of course we could have taken a 1/8 of an inch or a 1/4 of an inch microphone, and that would have given probably a little bit more in the frequency, maybe up to 30 kilohertz or so. But we have decided not to do that because it's a little bit of an overkill. So any more questions? Well, in that case, I would like to thank you for your attention, and I hope that you have learned something in this 1 hour session. And next time, I hope to see you in real life, not being behind the screen. So thank you very much, and see you soon, I hope. Bye-bye.